Okay, so today we're going to go over the extreme value theorem. And in the extreme value theorem, this is something we can apply to a continuous function on a closed interval. You can still do the procedure even if those criteria are not met in order to determine mins and maxes. Now, an extreme value theorem can guarantee that we have an absolute min and an absolute max on an interval because it is continuous and because it's on a closed interval. But since the extreme value theorem focuses a lot on absolute mins and absolute max, otherwise known as global mins or global maxes, I want to go over with you what relative min and relative maxes are so that we could kind of understand the difference between them. Okay, so I'm going to draw this figure, and please draw it along with me. So let's say we have different x values, okay, from A through E, and your graph looks something like this. Okay. Now, there wasn't supposed to be a wiggle here, so we're going to try drawing that section again. A little bit better. I don't need to have that far out. Nope, that still doesn't look right. Okay, I'm going to try one more time. Okay, better. So, over here, this is when x is A. Over here, this is when x is B. And I try to draw it so you have like a line segment to maybe a straighter line segment, and then it becomes kind of a parabolic curve down here when x is C. And over here it becomes straight and then curved. Okay, so I'm kind of emphasizing when x is equal to b is non-differentiable. And the reason for that is that it's a corner. And when x is equal to d, it's also non-differentiable, but I was trying to draw it as a cusp. So we see non-differentiability. So it's important to know where your function is non-differentiable, because that could possibly be a point on the graph. Now, I actually just realized something here. So I'm going to draw it in a y-axis, so that I can kind of refer to this height here, and this height is supposed to be lower. Okay, that's important because we're going to talk about, as far as this function is concerned, it is a closed interval. There is guaranteed by EVT to have an absolute min and an absolute max. So it looks like at x equals A, we have that absolute or global max, okay, for the whole function, because it's this lowest y value, and the highest y value is when x is equal to d. I said the wrong thing. X is equal to A, it has the lowest y value, so it's an absolute min. I got ahead of myself. Let me correct that, min. And x equals d is the absolute max, or global maximum point, okay, because it has the highest y value. So that kind of takes care of these 2 points, okay. But when you talk about relative extreme points or local extreme points, okay, it's talking about a point within the domain of a function, and it's considered like maybe an interior point. So let C be an interior point of the domain of F, then F of C is a relative maximum point at C if and only if the function f of x falls before the y value, or is equal to y value, for all x in some open interval containing C. All right, so believe it or not, x equal to D is also a relative maximum point. Okay, because on some interval, maybe this one, it is its relative or local maximum point. Now, with that being said, let's move on to relative minimum. On the domain, if and only if the function is larger than the y value or equal to the y value for all x in some open interval containing C. So if it can equal, then you can actually take a look at this part and say that x equals to a is a relative minimum on some interval. Okay? So it may not be the minimum point of every point, but that happens to be the case because it's also the absolute min. All right, so other relative extrema that we have here. So believe it or not, let me clarify this, okay, we have what is considered a relative maximum point when x is equal to b. It's the highest y value on some interval, okay? And the same thing with C, well, it's not a max. X equal to C is a relative minimum point on this interval, perhaps. So that's why it's the word local, or relative to which interval you're looking at. And we've already discussed when x is equal to D. So let's talk about x is equal to E. So since this is going down over here, we can say that x is equal to E is a relative minimum point. Okay? So there's your differences between absolute min and relative min, absolute max, relative max, and similarities. Now, I'm also pointing this out because we had this procedure written down yesterday. Let me take this part off since we're done with it. And I'm going to go over how it kind of ties into what we just discussed. Okay, so it's important to find the derivative, okay, because we have relative mins and relative maxes, okay, when we know the slope of our tangent line is 0. This is a horizontal tangent, okay, but that's part C. The reason we have part B here is because if you look, it's talking about where f prime of x is not defined. That means where it's non-differentiable. And if you can look at your graph, it was non-differentiable at x equals b, okay, and x is equal to d. So at x is equal to b, it turned out to not be an absolute max, but it was a relative max. It was still a maximum point. Now, x equal to d did turn out to be your absolute max. So we always have to check those x values where it's non-differentiable, because it's quite possible that's where your absolute min or your absolute max is. Okay? Now, C is what I was talking about before. If your derivative is equal to 0, you're looking for where you have your horizontal tangents. And that can also be where you have a absolute min or absolute max. Now, in this particular case, it turned out to not be an absolute min. It was actually just relative min. I'm sorry, down here. And so you still have to check there, and that's why we have parts B and C. So how do we check as part D? You now know what your list of X values are. You plug them in to find the Y values. And then once you know what they are, you compare them. As I was discussing, your highest Y value would be your absolute max, and your lowest Y value would be your absolute min. Okay? And then we would state exactly that. So we're going to do an example together now that we understand everything. Okay, so find the extreme values of the function on the given interval. So since f of x is 2x minus 3x to 2/3 power, this is a continuous function, and we were given a closed interval, we can say that EVT applies. Okay, so we're guaranteed to actually find our absolute max and our absolute min. Okay, so let's go through our steps. A, we're going to find the first derivative, so f prime of x would be 2 minus 2x to the negative 1/3 power. B, okay, whenever you have to find your min or your max, please do steps A through E. You need to have them all, because when you take the AP exam, they're looking to see if you checked where it's non-differentiable, all your critical points and stuff like that. So doing all these steps guarantees that you get full credit. All right, so speaking of non-differentiability, we're going to look at our function for f prime of x. Now I rewrote it so we can see where it's non-differentiable. So x cannot be 0 because you'd be dividing by 0. So it turns out that x equals 0 is a critical point. Okay, so that's important. Let's move on to C. So now we're going to take our derivative and set it equal to 0 to solve. And when we go to solve this, okay, we end up, you could cross multiply, that probably makes it easier. The cubic root of x would end up being 1, and that is just one answer when x is 1. So when x is 1 is also a critical, it's not coming up. Let me write it here. I'll work this way. Okay, so then I'm going to erase part A so we can start working up there. Okay, so we have these two critical points when x is 0 and when x is 1. Now, if you remember yesterday, we also spoke about not only the interior points for our function, but our end points of our function. They need to be tested too to see if they're an absolute min or an absolute max. In the diagram I had before, x equals a was an endpoint and it was the absolute max. Absolute min. So you always have to check your endpoints. Please make sure you check your endpoints. So we need to check when x is negative 1 and when x is 3 and what are our critical points, which happen to be interior points. So please make sure that you have this to be checked. Okay, it's not just your critical points. You may not have any critical points. Okay, so you always have to check your endpoints. So once you actually plug this into your function, okay, then you can list the answers. You don't have to do the substitution. The point of this step is actually comparing your y values. Coincidentally, because we have 2x minus 3x to 2/3 power, we need our calculators anyhow to get this answer for f of 3. So that's why I'm not showing the work for substitution here. So this is part D. Okay, E is to compare them and write an answer. So let me erase this. You should have had it. Okay. So in this case, we can say by EVT, there is an absolute max and absolute min. And we can say f of x has an absolute min, or max, whichever you want to start off with first, at x equals. So the lowest y value in this particular case is the -5. So here's your absolute min. And we say because it has the highest, because it has the lowest y value, and f of x has an absolute max. Okay, so we're looking for the highest y value. And believe it or not, it's when y was equal to 0. So because it has the highest y value. Okay, so it turned out that I wrote the wrong answer. I was looking back that an endpoint when x is -1, so please correct this. This is what happens when you don't have your coffee in the morning. So when x was -1, it was the absolute min. So it was an endpoint that was an absolute min because it had the lowest y value. Okay, so always double check your answers. That's always a good lesson to have. And f of x has an absolute max at x equals 0, so this was an interior point, okay, because it had the highest y value. All right, we're done. Good luck. Remember to check your answers. Make sure you have all the steps. When you're taking your notes, make sure you have problem work and answer. Good luck.